All right. So before we get going, just want to let everyone know that there is a short evaluation for this course that I would ask you to all please fill out when you have a chance at the very top of the modules in Canvas. So next time you're in Canvas, if you can just click on that, probably takes like 5 to 10 minutes. It's not that long. So they are anonymous. I get the feedback eventually from my supervisor, but there's no names attached to it, so I won't know who wrote what. So if you write something nice or something critical, that's totally fine. I welcome your feedback. And also, whatever you want to say, you're welcome to say. But please do fill it out. It's kind of the only it's kind of the only what's what I'm looking for feedback I really get during the year, other than people like just telling me things outright. So please do that when you have the time. Before the end of the quarter, specifically before the end of finals. You have through finals week, but obviously sooner is better. That said, what did y'all do in class yesterday? We talked about the Leslie Matrix. Okay. And then I don't know. I imagine tomorrow you'll also cover new material.
He said that it should be reading till yesterday's class.
Okay.
Try to introduce something but he didn't have time to finish. And then I went after him and he said through 8.6.
Six. Okay. I have to remind myself what 8.6 consists of. Unfortunately, don't have that knowledge off the top of my head. Let's take a real quick look here, just so I can remind myself. Let's see one thing. Probably just easy. Take your time. Oh yeah. Sorry, I just wanted to see it here. 8.6 is okay, but not any eigenvectors or eigenvalues. Okay, oh yeah, we're good. Okay. Right, we kind of already talked about that a little bit. Right, okay. Sure. Yeah. What's that? Yeah, that's part of it. Yeah. Okay, where to begin? I guess you talk about Leslie matrices. That said, I'm also happy to, if people have questions about the test 3 practice problems that he posted, I'm happy to also address some of those. But let's talk about Leslie matrices a little bit, specifically looking at this handout that I gave you all on Tuesday, right? Thursday. Did anyone get one of these? Or I should say, did anyone not get one? Cool. So, yeah, let me grab that. Sorry, I'm just trying to. Oh, you're here too. I think we kind of, yeah. Okay, okay. So let's go ahead and go. So, oh, you might want to see the things, right? Right, sure. And oops. Great. Oh my gosh. And here's the attendance form as usual. Also, actually, so one other announcement, which is moderately unfortunate, actually, is that I will not be able to have class next Thursday. Sorry about that. I have a funeral to attend in Los Angeles, which, yeah, so I would rather be here for all the reasons. Like, I wish the funeral wasn't happening, but not because I don't like the person, because I wish they weren't dead. But you know what? You don't always get what you want. So I won't be here Thursday or Wednesday, so we won't have class. I'll try to I think my plan is to try to before then come up with some sort of practice final, which unfortunately will not be as similar as the practice midterms I've come up with because I don't have a final of his to work from. So I'll try to come up with something and try to post solutions, try to make a video. So like instead of coming to class on that Thursday, there'll be a video of me going over solutions. That's the hope. I'll do my best. There's only so much time. Let's look. So let's say so anyway, so no class next Thursday. We'll still have class next Tuesday though. And we can do whatever you all want to. Oh, I know. So on Tuesday, we'll probably have to go over all the eigenvalue and eigenvector stuff because that is the stuff that you actually need to know going into 17C is how to find eigenvalues and eigenvectors specifically of 2x2 matrices. We don't really care about any larger matrices. I hope he doesn't talk about larger matrices. I don't know if he will. I imagine he won't, but actually, if he does, it won't be till Wednesday anyway, right? Because you guys won't be talking about that tomorrow, I hope. And we'll be talking about it on Monday because you have a test. So it'll be Wednesday and or Friday. All right. So let's go and look at this handout. It's decent. Let's see what there. So assume a population is divided into 3 age classes at time equal to 0, where we're using this notation here, n sub x of t is equal to the number of females of age x at time t. So your vector or your matrix, so you can call it either one when it's a 3x1 or 4x1, or essentially if it's only one column, we often just call it a vector instead of calling it a matrix. It's both. This matrix is just the number of 0-year-olds, the number of 1-year-olds, the number of 2-year-olds. So let's see what our setup is here. Let's assume that 20% of the 0-year-old females survive to age 1, 70% of the 1-year-old females survive to age 2, and all of them die after year 2. Oh well. Additionally, we are saying apologies. Let me grab something here. Additionally, or not additionally, what we're saying here is that, apologies. We're also, I skipped the whole line, apologies. So we're right here. So the way we write that mathematically is to say that the number of 1-year-olds next year is equal to 0.2 times the number of 0-year-olds in the previous year, or this year, I should say. So t plus 1 is next year, t is this year. Similarly, the number of 2-year-olds next year is 0.7 times the number of 1-year-olds this year. Right, so we're just writing the things we just said mathematically. Usually with these problems, you're told how many of each age category survive to the next age category, and you're also told how many offspring each age category produces. That's the next line here. So it makes sense that for the next generation, the number of 0-year-olds equals the number of offspring from the 1-year-old and 2-year-old females. 0-year-old females are not mature enough to reproduce in this example. And assume that 1-year-old females have an average of 3 female offspring and 2-year-old females have an average of 2 offspring. So the number of 0-year-olds offspring next year is going to be 3 times the number of 1-year-olds this year plus 2 times the number of 2-year-olds this year. That's what that's saying mathematically. So now what we're going to do is instead of writing all this in all these equations, right? So I should point out for these systems of equations, because oh my God, the words just don't want to roll off my tongue today. These 3 equations represent a system of equations, but we're going to write that as a matrix instead. So we're going to say, well, we know that the number of 0-year-olds next year is 0 times the number of 0-year-olds this year, plus 3 times the number of 1-year-olds, plus 2 times the number of 2-year-olds. So that row is dotting with that column. And you're getting 0 times the number of 0-year-olds, plus 3 times the number of 1-year-olds, plus 2 times the number of 2-year-olds. And then how many 1-year-olds will there be next year? Well, we know the number of 1-year-olds next year is 0.2 times the number of 0-year-olds this year. So it's 0.200. Right? Because you can't get 2 1-year-olds next year from the 1-year-olds this year or the 2-year-olds this year. They're going to be older.
Right.
Oh, yes, someone's turning off the radio outside. Okay, we can ignore it. And finally, the number of 2-year-olds next year is going to be 0.7 times the number of 1-year-olds next year. So you've got 0, 0.7, and 0. Typically, what I've noticed with these Leslie matrices, from doing this for a few years, is that basically the things you get next year are always the entries right below the main diagonal. And usually the main diagonal has all zeros, because if there was something on the main diagonal, you'd be saying the X-year-olds this year contribute to the same age group next year, which wouldn't really make sense because they're getting a year older. So usually, not always, there's some counterexamples, the main diagonal is all zeros. And the first row is usually going to give you, or where we're going to put the things that become offspring next year. So next year, there's going to be 3 times as many 1-year-olds and 2 times as many 2-year-olds for offspring, because each 1-year-old is producing 3 and each 2-year-old is producing. All right. And so just as a, just to remind you all, these just represent equations, right? This first equation is really just, I'm really just going to write, in fact, let me just not write it all. So this first row is just this equation. That n0 of t plus 1 is equal to 0 times n0 plus 3 times n1 plus 2 times n2. And this second row is just this equation. And the third row is just this equation. All right, so now we're going to actually throw some numbers at it. So assuming we have a starting population of 2,000 females of age 0, so I'm saying that, great, we know that n, actually, I'm sorry, I keep, brain. Starting population of 2,000 females of age 0, 800 females of age 1, and 200 females of age 2. How many females in each category after 1 year? So this is the number after 1 year, and it's going to equal this matrix 0, 3, 2, 0 0.2, 0, 0, 0, 0 0.70, multiplied by the number of females in the 0th year, or I should say year 0, because 0th year sounds like I'm talking about 0-year-olds. So there's 2,000 0-year-old females in the beginning. There's 800 1-year-olds, and there's 200 2-year-olds. And now we're just going to do the multiplication. I can zoom in a little bit. So doing the multiplication, we get 0 times 2,000 plus 3 times 800 plus 2 times 200. And for the second entry, we get row 2 dotted with the column 0.2 times 2,000. Plus, it doesn't matter. 0 times something plus 0 times something. And for the third entry, it's going to be 0 times 2,000 plus 0.7 times 800 plus 0 times 200. Simplifying our numbers here, we get 2,400 plus 400, which is 2,800. We get 0.2 times 2,000, which is 400. And 0.7 times 800 is 560. And then every subsequent year, we just multiply by that matrix again. So for year 2, we're going to say that n0 of 2, n1 of 2, n2 of 2 is going to equal that same matrix 0, 3, 2, 0 0.2, 0, 0, 0, 0.70, multiplied by this result here. This is our, this is everything. This is our n of 1 vector. So that's going to go right here. And we're going to have, actual numbers, James, 2,800, 400, 560. Multiplying this out, we get 0 times that plus 3 times 400 plus 2 times 560. And then we have 0.2 times 2,800, which is, I think it's 560. Yep. And then 0 times that, 0.7 times 400, which is 280. So we end up with 2320, 560, and 280. So after 2 years, we have 2,320 0-year-olds, 560 1-year-olds, and 280 2-year-olds. And if you want to find out how many you had after 3 years, you would multiply by this matrix again, 4 years again, 5 years again. So something we often ask is how many after, say, sure, 20 years. We're not actually going to do the math. We're just going to say, well, if we call this matrix, actually, I don't even want to give the name. I would just say that our n of 20 is going to equal the matrix that we have 0, 3, 2, 0.2, 0, 0, 0, 0.70,
raised to the 20th power times our initial year zero vector of 2,800 and 200. And kind of what we're building up to with these Leslie matrix examples is how you actually easily in quotes, how you more easily than just multiplying out a matrix times a matrix times a matrix times a matrix 20 times, how you easily raise a matrix to a power. And there is a process for that, which I intend to talk about on Tuesday. Hopefully. Also, you're always welcome to ask questions. Yeah.
800, 400, 500. I mean, like.
Yeah, sorry, so it's 2,800, right?
Oh.
I know it looks kind of gross right there. That is 2,800, believe it or not. Yeah. That make more sense now? Cool. All right. Okay. Let's look at another example. Did I give myself a two-sided print? I sure did. All right. So I feel like I had one-sided printouts somewhere, but I lost them. For the following Leslie matrix, how many age classes are there? Yeah. Now, this one's easy because the number of rows, number of columns are the same, but generally the number of age classes should be the number of what? Is it the rows or the columns? I'm not even sure as I think about it. Like, so let's think about it. If we were to multiply this by our age classes, let's just say they're like n0 of t, and 1 of t, and 2 of t, and n3 of t. Well, it looks like we need 4 rows to make sure that each row hits each column. So more generally, the number of age classes is the number of rows of our Leslie matrix. I think, although you could probably come up with something wacky, but I think almost always a Leslie matrix is going to be a square matrix anyway, so it shouldn't be an issue. But yeah, number of rows if you happen to be given a matrix that isn't square. All right, interesting question here. What percentage of 2-year-olds survive to age 3? So I actually think it's really good to write this matrix here because then I can think about, okay, when I do this multiplication, I'm going to get the number of 1-year-olds. The number of 0-year-olds next year, the number of 1-year-olds next year, the number of 2-year-olds next year, and the number of 3-year-olds next year. So I'm trying to figure out, what percent survive to age 3. I'm trying to figure out what's ending up right here in the age 3 spot in my resulting output. So to get that last bottom row entry, it's going to be the bottom row dotted with this. So it's going to be 0 times that, 0 times that, 0.2 times that, and 0 times that. So it's going to be 0.2 times n2 of t, or in other words, 20% of 2-year-olds survive to age 3. That stuff all over the place here. Okay. What is the average number of female offspring of a 1-year-old? Okay, so now we're asking how many offspring we get. Well, that I should say, that's not the whole question, but that's the beginning place. I'm sorry. I'm thinking, okay, how many offspring do we get? Well, I'm looking at the first entry here, and the number of offspring, just in general, next year is going to be 1 times n0 plus 2.5 times n1 plus 3 times n2 plus 1.5 times n3. So if we're specifically asking about 1-year-olds, we're right there. So each 1-year-old is going to produce, on average, 2.5 offspring. So 2.5 offspring on average for each 1-year-old. Yeah.
I know it's 3.5 and not like 200% of like 1-year-old.
Well, So if you wanted to change it to a percentage, you would multiply 2.5 by 100, and you wouldn't get 205, you get 250. So you could say 250%, but it makes more, we usually talk about these averages as number of things, not percentage. So yeah. Basically, it's whatever the coefficient of that variable is, right? N1, the coefficient is 2.5, so it's 2.5 offspring per every 1-year-old. In a similar way, we say that every 2-year-old produces on average 3 offspring, every 3-year-old produces on average 1.5 offspring, and every 0-year-old produces on average 1 offspring. Yeah. It's assumptive. If we're not given anything, we assume 0, 1, 2 up until however many rows you have. But yeah, they could say something different, right? They could with words give you a setup where you started with 3-year-olds and went like 3, 4, 5 or something. But it's usually some base age, most often 0, and then every year after that. And it's just kind of the usual setup. It kind of has to be that setup because if you're talking about offspring, you're not producing offspring that are 7-year-olds, right? You're producing offspring that are 0-year-olds. So you kind of have to start at 0. You don't really have a choice. So yeah, if they don't tell you or it doesn't seem like it's given, you should just assume it's 0, 1 up to whatever last age category you would have. All right, let's look at this next one here. Assume that the population is divided into 4 age classes and that 65% of the females age 0, 40% of the females age 1, 30% of the females age 2, survive until the end of the next breeding season. Okay. So let's write down our matrix. And actually, here's what I would really encourage you to do. Write down the matrix. It's going to be a 4x4 matrix. And I know that I'm multiplying by the number of 0-year-olds, the number of 1-year-olds, the number of 2-year-olds, the number of 3-year-olds. And let's write down what we're supposed to get. So the first part is telling us how many survive to the next year. 65% of the females age 0 survive to the next year. 40% of the age 1s, 30% of the age 2s, and usually the last age group, 0 of them survive, right? None of them survive till the next year. That's typical, not always true though. Right, but see, they didn't even say anything about the age 3 people, so the age 3 people don't make it, they don't stay age 3 and they don't survive to age 4 because we don't have an age 4 category. So here's what that tells me here. I know that in my resulting thing, I need to have, let's see, 65% of the females age 0 make it to age 1. So I should end up with a 0.65 times the age 0s from last year. And 40% of the females age 1 survive to age 2. So the age 2s next year, right? So I should write this way. Sorry, this is equal to n0 of t plus 1. And 1 of t plus 1, and 2 of t plus 1. I'm doing more work than we need to, but I think it's going to help us see what's happening. So the age 1s next year is 65% of the age 0s the previous year. And the 40% of the females age 1 survive to age 2. So my age 2s next year are going to be 40% of my age 1s in this year. And finally, my 30% of age 2 survive. So my age 3s next year are going to be 20% of my age 2s in the previous year. What that tells me is what I need to have in rows 2, 3, and 4. In row 2, I better have 0.65 in the first column and then 0, 0, 0. So that multiplies that to give me that. And then in my second row, sorry, my third row, I haven't dealt with my first row yet. In my third row, I need a 0 and then a 0.4. So that the 0.4 multiplies the n1 and I get 0.4 times n1. And then 0 and 0. And finally, for my last row, I need a 0, 0, and then a 0.2. So that 0.2 multiplies the n3, sorry, multiplies the n2 to get 0.2 times n2 for my next year's n3. As I said before, when you're writing down like each age classes, how much of them survive till the next year, it's almost always all those slots directly below the main diagonal. And then they also tell us, assume further, that females age 1 have an average of 3 female offspring. So I'm going to have 3 times the n1s Females age 2 have an average of 7. So I'm gonna have 7 times the N2s. And females age 3 have an average of 4. So I'm gonna have 4 times the N3s. So that means I need a 3, a 7, and a 4, and then a 0 in the first spot there. So that I get 0 times N0 plus 3 times N1 plus 7 times N2 plus 4 times N3. Exactly like that. So there's the matrix we were looking for. 0, 3, 7, 4, 0.65, 0, 0, 0, 0, 0.4, 0, 0, 0, 0, 0.2, 0. Cool. You don't have to show all this work for this. I'm just writing it because I think it helps us see how we are figuring it out. And then the next question, which is really just doing some matrix multiplication. If at time 0, the population consists of 1,500 zero agers, 500 age 1. Notice I'm leaving myself on the left, some space on the left here to multiply by the matrix. 1,250 age 2, and 50 females age 3. Find the Leslie matrix and age distribution at time 2. I feel like the Leslie matrix is just the matrix. I don't feel like, I did something stupid. Not stupid. So I didn't read the question carefully. So I read the question as find the matrix. The question didn't say find the matrix. That's what the next one says. This question said sketch the matrix diagram. Not my favorite thing, but it's not hard to do. So we'll do that over here. We'll write the Leslie matrix here, and then we'll carry on over here a second. One second. Apologies. And really apologies, because I imagine he might ask you to sketch a matrix diagram. Oh, thank you. Thank you. I read that as 1,250. Good call. Make that a 0,250. That looks really stupid. Okay, but back to over here to our matrix diagram for a second. So our matrix diagram should have 4 circles with the age categories 0, 1, 2, and 3. So then I will point out none of these circles are going to have arrows pointing back at themselves because no age category contributes to itself in this example. In most examples, not every example. So here we're going to have 3 times the 1-year-olds, 7 times the 2-year-olds, and 4 times the 3-year-olds going into the 0-year-olds. And then we're going to have 0.65 times the 1-year-olds, times the 0-year-olds becoming 1-year-olds. We're going to have 0.4 times the 1-year-olds becoming 2-year-olds, and 0.2 times the 2-year-olds becoming 3-year-olds. Yep, that's how that should look. Now we can do the matrix multiplication, which again is really just mostly a test of your ability to keep track of things and to multiply correctly. So let's see, we have 0 times that, 3 times 500 is 1,500. 7 times 250 is going to be, oh, got a question.
I think 0.2, right? I'm not sure if I'm reading where this is 30% of the females.
Because yeah, you're right. Because you're 100. Because I missed the percentage there somehow. Good call. So it's a 30%, not a 20%. Yeah, I'm blowing it. Thanks. Good call. All right, now we can do the multiplication and get 3 times 500 plus 7 times 250, which is 1,750, plus 4 times 50, which is 200. And then the next row is 0.65 times 1,500, which is 650 plus 325 is 975. And then 0.4 times 500, which is 200. And then 0.3 times 50, which is 15. I feel like I'm making mistakes here. 0.3 times 250, not times 50. Gosh, yeah, which is 75. We should simplify this since we're going to have to do it again. It's probably going to be a little bit gnarly. So then our next one, so this is our N1. Sorry, our N of 1. I feel like the notation here is a little clunky, right? The subscript is the age category. The input in the parentheses is the age, the year iteration. So, right, this is our population sizes at year 0. Here we have populations at year 1. And then our populations at year 2 are going to be still our Leslie matrix again, 0, 3, 7, 4, 0 0.65, 0, 0, 0, 0, 0 0.4, 0, 0, 0, 0, 0 0.30 times that vector we just found, which is going to be 3250, 3450. And then we have 975, 275. So multiply it all out, it's probably going to get a bit gross. So this is where, if this was the last iteration, here's how I would answer this question. I would just write out the multiplication. Okay, cool. It's going to be 3 times 975 plus, okay, 7 times 200 is 1400 plus 4 times 75 is 300. And then next row is going to be, yeah, I'm not going to do 0.65 times 3450. I'm just going to write 0.65 times 3450. And the next one's going to be 0.4 times 975. And then the last row is going to be 0.3 times 200. Okay, 0.3 times 200 is 16. Oh, sorry, you can say that. And then I would probably just leave it. Like if this was a test question, which again, the numbers seem a little gross for a test question, but if this was on the test, I would stop there and move on to other things. And if I had time and the expectation was to simplify, I would simplify. But I wouldn't do that first. It's really, really not important. There was a test question I wrote that was kind of similar-ish to this, where it asked you to find like the 4th iteration, but it also said not to actually multiply it out. So just to find like an expression for the population size after 4 years, not to actually find the values. Yeah.
And why do we find it out, simplify it, just put the exponent.
Right, exactly. So typically we like to call this matrix L. If I was going to write the expression for this for the population after 2 years, it would equal L squared times my initial population vector n of 0. I should probably actually write down what the matrix and the vector are, but that's the very generic idea there. All right. Have we had enough of Leslie matrices or not yet? I kind of have. So let's I'll point out that I do think these are worth doing. The next page of this has, that's solutions. I don't want to shoot. Oh, sorry. All over the place here. There we go. So the next page is just a kind of more of the same. Except it's a different kind of model situation, right? It's still the same idea in that you have people that have different states of things, and we're saying these people can move into this category in each iteration. Here, unlike the previous examples, it's not age groups, it's categories of risk of developing breast cancer. You can either be healthy, early, or late stage. And so people can move back and forth between stages, or stay in the same stage. So this one, I would encourage you all to take the time to do on your own. The solutions are posted, so I think that's worth your while. But I think we've talked about Leslie matrices enough. Let's look at the last page, though. Yeah, matrix, fine. Okay, it's probably worthwhile to construct some matrix diagrams. So for this 2x2 matrix, how many circles am I going to draw? 2, right? There's 2 rows. You can give them whatever names you want. Typically, if it's not specifically talking about age categories, we usually just call them letter names like A and B. So we call this A and this B. A being the first thing, B being the second thing. So this one here, in fact, I mean, honestly, I would probably, to me, the matrix diagram is the hard. I am not good at the matrix diagram. I'm like, which way does it go? I'm really thinking of like multiplying this by AB and getting back, let's see, 1 times A plus 7 times B. And then 4 times A plus 0 times B. So going into A, we have 1A and 7B. Going into B, we have 4A and no B's. So honestly, I feel like I have to do the matrix multiplication to be able to draw the diagram correctly. It's probably not actually true that you have to do that. I'm talking about me. Okay, so.
The bottom row, it's just like B,
Uh-huh.
B, and just coming to you.
Sure.
Whatever you're on that row.
Okay, I like that. So yeah, so the bottom row is what's going into the bottom thing. The top, so the rows are what's going into the thing, and the columns are what's kind of going into that. So like you could say in this first row, well, that's going into A, and then the first column is A and the second column is B, so it's 1 times A plus 7 times B going into A. Let's see if we can apply that logic for this next one here. Okay, so what's going into A? Well, the first row is going into A. The 3 of A itself, 0 of B, and 2 of C. So A itself is going into A 3 times, and C is going into A 2 times. Going into B, we have the second row, 2 of A, 5 of B itself, and 1 of C. Finally, going into C, we have the third row, so 8 of A, 4 of B, none of C itself. That seems right. I probably would still do the matrix multiplication to check because I'm just like, I'm a little paranoid to be honest, because I've screwed these up so many times. Let's see, we're going to get 3 times A plus 0 times B plus 2 times C. Yeah, that seems right. 3A plus 2C. We get 2A plus 5B plus 1C. We get 8A plus 4B. Yep, that looks right on. Okay, I feel good about that. So they shouldn't be too hard to come up with the matrix diagrams if you're given the matrix and vice versa. It should be not terrible to go back and forth between the diagrams and the matrices.
It'd be wrong to put times 0 themselves.
No, but it's unnecessary. It's like writing. It's like if you wrote every number you ever wrote raised, or if you wrote every number you ever wrote raised to the first power, or of the like every variable with a coefficient of 1. Like it's technically correct and super unnecessary. Okay. Let's look at the next thing. Inverses. So, important question here, or important the way this is worded. Determine if the matrices are inverses. They're not saying find the inverse, they're saying see if they are inverses, meaning if they're inverses, the matrices multiplied together should always give us the identity matrix, which is the 1s on the diagonal and 0s everywhere else. So if I multiply these together, let's see what happens. A times B is going to equal 1 times negative 7/3 plus 5 times 2/3. So negative 7/3 plus 10/3. And then 1 times 5/3 plus 5 times negative 1/3. So 5/3 minus 5/3. Looking good so far. 2 times negative 7/3 is negative 14/3. 7 times 2/3 is 14/3. Finally, 2 times 5/3 is 10/3. And 7 times negative 1/3 is negative 7/3. And yes, we do end up getting 3/3, 0, 0, and 3/3. So yes, they're inverses.
You just find the inverse of A and compare it to B.
Yeah, but I will say yes, but that's not really the intent. Also, no, I mean, yeah, if they're not inverses, you could do the same thing. But well, the thing is, if they're not inverses, it might be that both of them don't have inverses. And so then finding the inverse is not an option. So then you kind of have to do it the other way, or say the inverse doesn't exist. But definitely, the way this problem is written, the intent is to multiply the matrices together. So let's check the next one. A times B, my guess would be they're not going to be inverses because the first ones were. We should still check. Let's see, that's going to be 0 times 2 plus 1 times 1. And then 0 times 3 plus 1 times 0. And then 3 times 2 plus 2 times 1. And then 3 times 3 plus 2 times 0. The first row worked out. You get 1 comma 0, or 1, 0, there's no comma. The second row did not. You get 6 plus 2, and you get 9 plus 0. It's definitely not equal to the 2 by 2 identity matrix. So not inverses. So now, for this next question, definitely the process is intended to be multiplication of matrices, because I pray, hope, whatever you want, I hope he doesn't talk about inverses of 3 by 3s, or at least trying to find them, because it's a much more intensive process than finding the inverse of a 2 by 2. Okay. Determinant of 3 by 3 is no big deal. So I will say, you could, if someone asked you, so let's pretend like the question was different. Let's pretend like the question was, is this matrix invertible? A equal to 1, 0, 3, 2, 7, 9, 0, 2, 1. The way you can test if a matrix is invertible is by finding its determinant. If the determinant's 0, the matrix is not invertible, also called singular, meaning it's single, it doesn't have a partner that's its inverse. If a matrix is a determinant that's non-zero, it does have an inverse, even though we might not have the tools to find it. So let's actually answer that question first. For this one here, the determinant of A, we're going to find by, again, writing our matrix 1, 0, 3, 2, 7, 9, 0, 2, 1, and then tacking on the first column and second column. So 1, 2, 0, 0, 7, 2. We're happy to see that there's zeros here. It's going to make our computation easier. Determinant's going to be 1 times 7 times 1 plus 0 times 9 times 0 plus 3 times 2 times 2 minus the product of the diagonals in the other direction. 3 times 7 times 0, 1 times 9 times 2, 0 times 2 times 1. So calculating this, we end up getting 7 plus 12 minus 1 times 9 times 2, which is 19 minus 18, which is 1, which is not 0. So A certainly is invertible. It has an inverse, and now we're going to check and see if it's that. It probably is, but I don't know. Let's do it. Right, A times B is a bit more work here. So let's be certain back here. So multiplying first row with first column, or I should say dotting the first row with the first column, we get negative 11 plus 0 plus 12. First row, second column, 6 plus 0 minus 6, that's 0. First row, third column, negative 21 plus 0 plus 21, that's also 0. Looking pretty good so far. Second row, first column, negative 22 minus 14 is negative 36, plus 36 is 0. Second row, second column, I'm hoping for a 1. 12 plus 7 is 19, minus 18 is 1. Second row, third column, negative 42 minus 21 is negative 63, plus 9 times 7 is 63. Yep, we get a 0. Finally, that with that is 0 plus negative 4 plus 4. That with that is 0 plus 2 minus 2. And finally, that with that is 0 minus 6 plus 7 score. So yes. And for a 3x3, if you're given both matrices, there really isn't another way for us to do it. Yes, there is definitely a way to find the inverse of a 3x3 matrix. It's just not something we're dedicating time to. We don't care about 3x3 matrices. Okay, last thing on this page here, find the inverse of this matrix. So for a 2x2, we definitely have a process for writing the inverse. It's going to equal, and you should write it as A inverse, 1 over the determinant of your matrix A times you're switching the diagonal entries, you're changing the signs of the off diagonal entries. And then the determinant of A is going to equal 2 times 4 minus 1 times 5. I personally would choose to leave the 1/3 out in front, write it as 1/3 times 4, -1, -5, 2. But it's also fine to distribute the 1/3 to each term if that's your preference. If it was a non-fractional number, I probably would choose to distribute it, but that's just personal choice, really. Okay, so last time we started to talk about matrix equations a little bit, I think. Like we had one example at the end, I believe. Yeah, we did that one. So let's go a little bit further in that direction. Let's make sure I've got. I mean, not that these solutions aren't posted, but I still post them in the class. A million papers over here. Yes, there we go. Okay, so let's talk about solving. solving systems of equations. And actually, more importantly, just writing systems of equations. Because one of the important things about these matrix multiplication is that next quarter in 17C, we're going to be dealing with a lot of systems of two equations and two unknowns. And we're going to always want to write those as a matrix equation, but it's important to kind of still keep the connection between this matrix thing and the fact that it's representing this system of equations over here. So let's start off with something like the following. We're going to solve the system 2x1 plus 3x2 equal to 5, and x1 minus 5x2 equal to 9. You could totally solve this in a normalish way. That's not the point, but I'll point out that you could say, well, great, I'm going to say x1 equals 9 plus 5x2, and then you could jam that bit back in over here and say that 2 times 9 plus 5x2 plus 3x2 equals 5. 18 plus 10x2 plus 3x2 equals 5. I think the numbers work out nicely here. I get 13x2 equal to negative 13. So x2 equals negative 1. And then I can throw that back in over here and get x1 equals 9 minus 5. So x1 equals 4. So a system of two equations and two unknowns you can usually solve pretty easily. But first of all, we could have larger systems. Second of all, it's not the point. Because we really want, there's a lot of things that looking at the matrix is going to give us, and also our system is going to be a little bit different. So yeah, we'll say that. Well, actually, I'll say that in a second. But I'll point out we can write this as a matrix. Really loving the drilling over there. I'm sure you guys are too. Right, as a matrix equation. So there's going to be three pieces of our matrix equation: our coefficient matrix, our variable vector x, and what it's equal to, which we usually call b. In this case, our coefficient matrix A is going to be 2, 3, 1, negative 5. It is important that you write the variables in the same order so you can read the coefficients in the right order. Right? You want the x1s first, the x2 second. Multiply by the vector x1, x2 equal to the vector 5, 9. I really, really, really want to stress this equation, I should say this matrix equation, and this system of equations represent the exact same information. They both mean the equations 2x1 plus 3x2 equals 5 and x1 minus 5x2 equals 9. They're just written in different ways. But writing it as a matrix allows us to solve it in a different way by, if the matrix is invertible, multiplying both sides by the inverse. So let's see what happens. So I'll point out here that A inverse is equal to 1 over negative 10 minus 3 times the matrix negative 5, 2, negative 3. Sorry, I know I'm saying I'm switching the diagonals. So 2 and negative 5 switch places, and the off diagonals change signs. And I would probably do one small thing here. I do like when it's a negative out front to distribute the negative into the matrix. So I would probably choose to write this as 1 over 13 times 5, 3, 1, negative 2. That's just how I like to do it. I don't like to distribute that fraction. I don't think it's worthwhile. So now we're going to multiply both sides of this equation by the A inverse. So we're going to have 1/13 times 5, 3, 1, negative 2 times 2, 3, 1, negative 5 times x1, x2 equal to 1/13 times 5, 3, 1, negative 2 times 5, 9. In just matrix notation, what we're doing is we're saying, cool, A inverse times AX equals A inverse times B. As long as A inverse exists, right? It has to exist to be able to do this. And then on the left-hand side here, we'll check it out. I have 1/13 times 5 times 2 plus 3 times 1 is 13. 5 times 3 plus 3 times -5 is 0. 1 times 2 plus -0 is 0. 1 times 3 plus -2 times -5 is 13. Oh yeah, of course. This multiplication here is just the identity matrix, as it should always be when you multiply by the inverse. We just did like 3 examples of that. But on the right hand side, we're actually going to multiply it out, and we're going to get 1/13 times 5 times 5 plus 3 times 9 is 25 plus 27. And 1 times 5 plus -2 times 9 is 5 minus. So we end up getting the identity matrix times our vector x1, x2 is equal to 1/13 times 52, -13. Or, remembering that the identity matrix times anything is just the anything, we end up getting that x1, x2 is equal to 1/13 times 52 is 4. 1/13 times -13 is -1. The exact same values for x1 and x2 that we got doing it this way. Now, I showed every possible step here. I did way more work than you really want to do. The real work you would do if you're solving a problem like this is you'd be like, cool, you would just normally to solve a times x equal to b, just find a inverse, and then our solution is going to be x equal to a inverse multiplied by b. That's the idea. You don't have to show all the steps of multiplying both sides by the inverse, and then see you get the identity, and so on and so on and so on. You just jump straight to that. Yeah. 25 plus 27 is 52. And 5 minus 18 is -13. How much to say here? Yeah, we should talk about that for just a brief minute. So I'll point out that although we are mainly focused on systems of 2 equations and 2 unknowns, someone could ask you to write the matrix equation for a larger system. For example, I could give you the the system of equations, x plus 2y plus 3z minus 4w equal to 7, 2x plus 5z minus 7w equal to 8, y plus 4z plus 3w equal to -2. And then ask you to write the matrix equation for this. Okay. How many equations do I have? That's the number of rows. How many columns do I have? Or so how many variables do I have? 4, so that's going to be the number of columns. I feel like my papers are everywhere. Oh well. So we know it's going to be a 3x4 matrix. Now, I've kind of done something mildly terrible in that these aren't all lined up nicely, right? I've got XX and a Y there. So really, if I want to be careful here, I should think about the first column being just the coefficients of X. So it's going to be a 1, and then a 2, and then a 0, because there isn't any X in the third equation. For my second column, coefficients of Y, 2, 0, and 1. For my third column, coefficients of Z, 3, 5, and 4. For my fourth column, coefficients of W, -4, -7, and 3. Multiplied by the variable vector, the 4x1 vector that just consists of X, Y, Z, and W, equal to the result, the vector 7, 8, -2. Really, this is just a test of our understanding of, do we know how to write these equations as a matrix equation? But it works, right? If you actually wrote this out, you'd exactly have 1 times x plus 2 times y plus 3 times z minus 4 times w equal to 7. And you'd have 2 times x plus no y plus 5 times z minus 7 times w equal to 8. And no x plus 1 times y plus 4 times z plus 3 times w equals -2. So that's all that question is really asking about. there's a lot more to say there. I just wanted to point out that you could be asked to interpret a larger system of equations as a matrix equation. I don't think it's a really easy question once you know what you're doing. You just have to make sure you understand what you're doing. But like, I would be thrilled if you guys were asked this question in your test. It's almost 3 points. Right. I'm always doing so the coefficients of each variable always land in the same column for each variable. Just like in the previous example, which I've hidden from myself. Wow. Sorry, we can't find it. It's impossible. Here it is. Just like in the previous example, the columns all correspond to the coefficients of a particular variable. The first column is the coefficient of x1. The second column is the coefficient of x2. The first row is the coefficients that show up in the first equation. The second row is the coefficients that show up in the second equation. So columns correspond to particular variables, rows correspond to particular equations. We had something else. Oh, yeah. So there is something else that occurs here, which is somewhat noteworthy. Yeah. So we'll just address real quickly. What happens, especially in a 2x2 situation, if A is not invertible? So let's look at two different situations. Situation one. We have the system of equations 2x plus y equal to 7 and 2x plus y is equal to 5. So I'll point out, if we wrote the matrix equation would be the matrix 2, 1, 2, 1 times the vector x, y equal to 7, 5. This matrix certainly is not invertible. So notably, A is not invertible. The determinant of A is 2 times 1 minus 2 times 1, which is 0. In this case, what does this mean? Well, if you look at these equations, or if you solved each of these equations for y, you can think of this as y equal to negative 2x plus 7 and y equal to negative 2x plus 5. Those lines have the same slope. Those lines have different y-intercepts. Those lines are parallel. Those lines never cross each other. So there's no value of x and y that is a solution to both of those equations at the same time. So these are parallel lines looking something like this. And there's no solution to both equations at the same time. If you try to solve them, you're going to get nonsense, right? If you actually you set these equal to each other, negative 2x plus 7 equal to negative 2x plus 5. The negative 2x is canceled, and you get 7 equal to 5. Nope, not true. So sometimes, if your matrix is not invertible, that means you have no solutions. So what can happen here is, if the determinant of A is equal to 0, aka A is not invertible, we could end up with a system without any solutions. Or look at another situation here, which has a similar but very different result. Yeah. Let's say our system was the system, again, 2x plus y equal to 7. And now the second equation is going to be negative 4x minus 2y equal to negative 14. You might notice that my second equation is just my first equation multiplied by negative 2. If we write this as a matrix, though, we're still going to get 2, 1, negative 4, negative 2. We're still going to get a matrix A whose determinant is 0. So determinant of A, which is equal to 2 times negative 2 minus 1 times negative 4 is negative 4 plus 4, which is 0. So again, A is not invertible. But in this case, instead of having parallel lines, we have, what's the word I'm looking for? We have the same line. Right? We have a line, and then the other line is the same line on top of it. Meaning every point on the line is a solution to the system. So here we have infinite number of solutions. Because the lines are the same line. So every point on the line is a solution to both equations. For example, 3, 1 is a solution. I'm writing them as coordinates because I just want to. Or 5, -3. Or take your pick, 2, 3, right? There's literally an endless supply. But we can't say the solutions are all real numbers because that's not an accurate way of describing what the solutions are. The solutions are points on this line. So here, our solutions are all points x, y that satisfy the line equation. Y equal to 7 minus 2x. Or however you want to write it. So to sum up here, if your matrix equation has a matrix that is not invertible, that means you either have no solutions or infinite solutions. On the other hand, if your matrix is invertible, you get exactly one solution. Yeah. All right. Sure. Yeah. Okay. I think that's all I really had to say about that. Let me look here. Have any of you looked at the practice problems he's posted? It's okay if you haven't. I'm really just curious. So I'm just looking here to see if I see anything notable here. Finding. So let's kind of talk through this since I think he's not like putting super crazy stuff on here. Also, if you have questions, you're always welcome to say, hey, James, what about this? So let's take a look. As usual, right, there's like a million things on this, right? Because why would you self-edit? Why do you? I mean, I get it. You want to give lots of examples in practice. So let's look at the following. Use a rotation matrix. Have we talked about that? I don't think so. I wouldn't say. Find the cosine of the angle between the given vectors. Definitely that's something he could and probably will ask. I would remember or remind you that cosine of an angle is equal to the dot product of the vectors divided by the magnitude of the vectors. U is the vector with initial point that and initial point that, and V is the vector with that and that. Oh, sorry. All these are finding the cosine of the angle. I'm like, what? So what are we doing with U and V? Good question. We're finding the cosine of the angle. So I'll point out that here, before you can do the problem, you have to like find the vectors. So for this one, right, U is going to equal 2 minus 1, 0 minus -2, -4 minus 3. And V is going to equal terminal minus beginning, so -1 minus 2, 1 minus 4, and 2 minus -3. So to make sure if your vectors are given as what you get by starting somewhere and ending somewhere, you have to do the ending numbers minus the starting. Yeah. U is a diagonal of a cube and V is one of its edges. This problem is more about your ability to draw the thing in a way that's helpful. So if you draw a cube and put one of its corners on the origin of your theoretically coordinate system, and then you draw I would pick sides that were length 1. So we're being asked to find the angle between the diagonal of the cube, which is like from 0, 0, 0 to 1, 1, 1, and one of its edges. I would pick maybe this edge here, the vector, which gives you the vector 1, 0, 0. So the diagonal we could think of as the vector 1, 1, 1, and one of its edges you could think of as the vector 1, 0, 0, or 0, 1, 0, or 0, 0, 1. Either one of those three is fine. And then dual process, dot product divided by the magnitudes, that's your cosine. So this one, but that one's not so much about knowing the formula, it's about knowing how to set up the picture the right way and then make choices about what the vector should be. You can pick a different length, edge length, but one is pretty typical. Because it's the easiest place to start from. I didn't like you could have actually started from anywhere you wanted, but if you have a choice, you almost always want your vectors to emanate from the origin, whether it's in 2 dimensions or in 3 dimensions. That's a good question. For what values of b are the vectors 2, 6b and b squared b orthogonal? Sure. So what do we need to be true for orthogonal vectors? Right. So we're going to say that 2 times b plus 6 times b squared plus b times b equals 0. So yeah, I'm going to say something extra here, but fine. So we solve this. We have 2b plus 7b squared equal to 0. You can factor out a b. And you either get b equal to 0 or b equal to negative 2 over 7. Now, what I want to point out is that normally when you're asked a question about finding orthogonal vectors, we exclude the 0 vector from our possible solution. Not because it's not orthogonal, it's because it's orthogonal to everything. So it's kind of a boring answer. So usually also, we often ask you to find it as a unit vector, and the 0 vector can't be a unit vector because it doesn't have any length and you can't make it length 1 magically. So usually if you're answering this question, you should give the answer that gives a non-zero vector. A more interesting question, I think, is if I give you this vector, 3, 4, 5, find the vector that's orthogonal. There's lots of choices. Here's the easiest way to do it. Pick 2 of the components. Interchange them and change the sign of one of them. So I'm going to pick 3 and 4. I'm going to interchange them and make one of them negative. And then the last component, make it 0. Totally valid. That will definitely be perpendicular to V because the dot product of those things will be 12 plus negative 12 plus 0, which is 0. But you could have made a bunch of other choices. You could have picked, I don't know, interchange the second 2 and say it's going to be 0, comma, negative 5, 4. That would also work to be perpendicular to that vector. So when you have a 3-component vector and you want to find something that's perpendicular to it, interchange 2 of the components, change one of the signs, and make the missing component 0. Because these 2 and these 2 dot to 0, and then as long as you put a 0 there, that will definitely also dot to 0, and then 0 plus 0 is 0. Let's see, rotating stuff. Just trying to look through here. So there's lots of questions. So yeah, lots of questions. Right. So 0 or negative 2/7 would make that correct.
That one that you were doing is what question?
I just made it up.
Okay.
How do you solve for a matrix EX that equals 0 even though I multiply by anything you get?
Yeah. Oh my gosh. Good question. That feels like something worth looking at. So we want to solve B, 1, 1, negative 2, negative 3, negative 3, 6, 2, 2, negative 4, times x1, x2, x3 equal to 0, 0, 0. I don't feel like he's talked about this in class really at all. Because the problem doesn't just say find a solution. There's definitely a solution. 0, 0, 0 is one of them. That's not the only solution, but it is one. So here's what I'd observe in this example. And again, I'm not really sure how much we should get into this because it's kind of getting into territory that I don't think he really needs to be getting into. But I would point out that this system, so I should say, this system of equations represents how many equations? How many variables? Also, right? Square matrix, number of equations, number of variables are the same, which in this case is 3. So here are my 3 equations. x1 plus x2 minus 2x2 equal to 0. Negative 3x1 minus 3x2 plus 6x3 equal to 0. And 2x1 plus 2x2 minus 4x3 equal to 0. And what you should observe is that each of these equations is a multiple of the other ones. The second equation is just negative 3 times the first equation. The third equation is just 2 times the first equation. So really, just like with the parallel lines examples, these 3 equations all represent the same equation. So there's really only one equation to deal with here. All this boils down to really just saying, cool, the first equation, x1 plus x2 minus 2x3 equals 0. The problem here is that we have one equation, really, and 3 unknowns, which means there's going to be an infinite number of solutions. And the way to write the solutions is kind of super annoying. Again, I don't think that's something we really should get too into, but I'll talk about what we do here. So when you have more variables than equations, some of the variables are what we call free variables, usually the ones further to the right. So I have 2 more variables than I have equations. I have 2 free variables. So what we would say here is that x2 and x3 can be anything we want. But then, once you've chosen values for x2 and x3, x1 is fully determined. Whatever x, like if x2 is 7 and x3 is 1, we know that x1 has to be negative 5. Right? There is no choice left. So you have 2 choices, 2 free variables, and 1 not choice that's already determined. So what we're going to do is we're going to say, cool, and for some reason, we like to pick these other letters. So we're going to say, let x2 equal r and x3 equal t. Usually letters r, s, and t are picked for these parameters. And then x1 is going to equal negative x2 plus 2x3, which is negative r plus 2t. And then you could write this as a vector, as a linear combination. You could say the vector x is equal to r times the vector negative 1, 1, 0 plus t times the vector 2, 0, 1. So any solution to this equation looks like a multiple of this vector plus a multiple of that vector. Again, I don't want to get too, I feel like I've already gotten too deep into this. Like, I don't think this is going to show up, but I didn't feel like it was the time to not answer the question. So that's kind of what's going on with that question. But again, I really, really, really don't think that's come up in class, right? Yeah. Something people copy and paste problems from other things. Like, yeah, this will be good. And they kind of forget that they've asked something that they didn't mean to ask. That happens. There was something on here that I thought was, oh, there's like a bajillion things in here. So I will point out, you should be selective when you look at this, right? Not every problem is a good problem to do. Don't do those. If you think something's probably not going to show up, I would skip it. I feel like there was something. Oh, I know what it was. Where'd you go? Sorry, there was something on here that I thought was. Oh, it's problem 3C. I feel like he might ask a question like this. Find an equation of the plane to the point 1, 2, 3. Plane through the point with normal vector, meaning perpendicular vector. Where'd you go? 1, 4, 1. Okay, the easiest way to do a problem like this is kind of like solving equation of the line in the y equals mx plus b form, where you're going to plug in the slope and then plug in your point to find the b value. So here we're going to plug in our slope, but our slope here is the coefficients of x, y, and z, which are the components of the normal vector. So our plane equation is going to look like the following. It's going to be 1 times x plus 4 times y plus 1 times z equal to some constant. And then to find the constant, just like you to find the constant b, you plug in the point that the line goes through to find the constant b. Here we're going to plug in the point the plane contains to find the constant c. So it's going to be 1 times 1 plus 4 times 2 plus 1 times 3 equals c. That's 1 plus 8 plus 3, which is a number. I think it's 12. Now we're not done because we actually still have to write the plane equation. So then our plane equation is actually going to be x plus 4y plus z equal to 12. The longer way of doing this, which is more like the point slope form of the equation, is to say that this normal vector dotted with any vector in the plane. Well, any vector in the plane, if that plane contains the point 1, 2, 3, and some other point x, y, z, then the vector from 1, 2, 3 to x, y, z is x minus 1, y minus 2, z minus 3. That vector in the plane and this vector normal to the plane have to be perpendicular, so the dot product has to be 0. Then your equation becomes 1 times x minus 1 plus 4 times y minus 2 plus 1 times z minus 3 equal to 0, which then leads back to exactly that equation right there. Either way is fine, but the first way is faster. All right, I think I've said enough. Practice exam right here. I will say this one I pretty much copied verbatim or rewrote verbatim from his practice exam video that was posted or that I had access to. So what I'm gonna do is I think there's one extra credit problem that I omitted part of because I didn't want to draw the weird picture for it, to be honest. But what I'll do is I'll post the solutions that he had already written so I don't have to rewrite them again immediately. But then I will try to find time tomorrow sometime to record a video of me going through the solutions so that you can actually, because I think, right, is the video helpful for that? Okay, yeah, okay. I thought so. I just want to make sure, yeah. So then I will take the time to do that sometime tomorrow and get that posted so that you can look at it over the weekend. All right, good luck on your exam on Monday. I think you'll all do fine. Just, remember to read the questions, right? If I could say anything, I've said it a few times, I think, but I'm saying it again. Make sure you read the questions carefully on your exam. That's probably the #1 easiest thing you can do to increase your likelihood of doing well. So read those questions carefully. Make sure you're understanding what is being asked and make sure you're not doing more work than you need to do. All right.